Okay, so in this video, we want to review how to obtain the decimal expansion of a ratio of two integers by hand. In other words, we want to review how to perform a division by hand. Let's start with a very simple example that illustrates really one key aspect of any division. So what if we wanted 9 over 6 in its decimal expansion? And that very first step, although here granted is rather trivial, is to look for common factors in both integers so that we can cancel and simplify our division. So if we factor, 9 is 3 times 3, and 6 is 2 times 3. Common factor of 3 which we can cancel, and not only can but should cancel, and we're left of course with 3 over 2. Now here's one way to obtain the decimal expansion in this case, as it is rather trivial, is to write 3 as 2 plus 1, and then separate. So we get 2 over 2 plus 1 over 2. Now 2 over 2 is 1, plus 1 over 2 is 0.5, and so in the end we get 1.5. But what if we had a more interesting fraction that wasn't so obvious? Well, let's redo this division, but in the correct fashion that would work for any ratio of two integers. So, let's do it here. 3 divided by 2. So we ask, how often, so how many times can we fit 2 into 3? The answer is 1. So 1 times 2 is 2. Then we subtract, we're left with 1. But now we're moving to the next decimal place, or I should say the first decimal place. To offset this shift, we have to then multiply this by 10. And we ask, and you'll see now we just repeat. So the first step was to ask, how many times can we fit 2 into 3? The answer was 1. Now the second step is, with 10 instead of 3, so we ask, how many times can we fit 2 into 10? And the answer, of course, is 5. 5 times 2 is 10. 10 minus 10 is 0. And whenever you have a remainder, a leftover of 0, this is the sign that you are done with the long division. And so 3 divided by 2 in decimals is 1.5. And again, this was a very simple example, but this idea works for the ratio of any two integers. Let's look at one more example. What if we wanted to perform 19, and I'll write it here, say 19 over 8. Well, 19 is a prime number. 8, well, sure it does factor as 2 cubed, but there's no common factor, so this fraction is reduced. So if we want its decimal expansion, let's perform it in this fashion. So we have 19 divided by 8. So same process as before. How many times can we fit 8 into 19? The answer, of course, is 2. 2 times 8 is 16. We subtract, left over of 3. Move to our first decimal place, but to offset this change, multiply here by 10. And we repeat now with 30 instead of 19. How many times can you fit 8 into 30? Well, the answer is 3. 3 times 8 is 24. We subtract, left over of 6. And again, we move now to the second decimal place, offset the change, multiply by 10, and we repeat. How many times can we fit 8 into 60? The answer is 7. As 7 times 8 is 56. Subtract, left over of 4. Move to our third decimal place, so multiply by 10 to offset this change. How many times can we fit 8 into 40? And the answer is 5, as 5 times 8 is 40. And once again now, as in the previous case, we have reached 0, which is the sign that in this case, our division is complete. So if we go back to the initial ratio, 19 over 8, in decimal form equals exactly 2.375. Now, a natural question to ask is, will we always reach a point where the number is 0? The answer is no. So here's a very simple example that you probably already know. Let me do it here, just to contrast. What if we wanted 1 over 6? So once again, the fraction is clearly reduced, as 1 and 6 don't have a factor. So let's perform our division. 1 divided by 6. How many times can we fit 6 into 1? Well, the answer is 0. We move to the first decimal place, offset by a factor of 10. How many times can we fit 6 into 10? Well, now we can. The answer is 1. 1 times 6 is 6. We subtract, we get 4. Move to our second decimal place, offset by a factor of 10. How many times can we fit 6 into 40? The answer is 6. 6 times 6 is 36. We subtract, we get 4. Move to our third decimal place, offset by a factor of 10. And at this point, you should find this interesting because in the previous decimal place, in the second decimal place, the number was 40. But it's 40 again, so it will be 6 again and again and again forever, right? 6 times 6 is 36. Subtract, you get 4, 40. So it will be 6 forever. So in this case, in the simple example of 1 over 6, we will never reach an end of our division. We will never have 0 because it will be 40 forever. So it will be 0.166666. And this will never stop. And one way of writing this is 0.16, and we say 6 periodic. The vertical bar above the 6 indicates to repeat the 6 for all other decimal places. So it's an infinite but repeating decimal expansion. So 1 over 6 is exactly 0.16 periodic. It has an infinite decimal expansion, but quite simple, 0.1 and 6 forever. Let's do one last example. And in this case, we will divide 4 by 7. And this may seem like a simple problem, and it is, but it also is very interesting. As in the case of 1 over 6, only one integer repeats infinitely often. Well, let's see what happens in the case of 4 over 7. So let's start. How many times can you fit 7, into 4? The answer is 0. Move to our first decimal place, offset by 10. How many times can you fit 7 into 40? The answer is 5. As 5 times 7 is 35. Subtract, you get 5. But now we're in the second decimal place, offset by 10. How many times can you fit 7 into 50? The answer is 7. As 7 times 7 is 49. Subtract, we get 1. Third decimal place, offset by 10. How many times can you fit 7 into 10? The answer is only once. 3, but again now, next decimal place, offset by a factor of 10. How many times can you fit 7 into 30? The answer is 4. As 4 times 7 is 28. Subtract, leftover of 2. Fifth decimal place, offset by 10. How many times can you fit 7 into 20? The answer is 2. As 2 times 7 is 14. Subtract, now we have a 6. Sixth decimal place, offset by 10. How many times can we fit 7 into 60? The answer is 8. As 8 times 7 is 56. Subtract, we get 4. Next decimal place, offset by 10, 40. And you might sort of be catching your breath here, but this is interesting. Because if you go back up So 40, previously 60, then 20, then 30, then 10, then 50, then aha, 40. So now we have a cyclic pattern. Starting with 40 gave us this decimal expansion. Now we're right back to where we began. So this whole string of integers will be repeating itself forever. And you can sort of try the first few numbers. You say, well, how many times can you fit 7 into 40? The answer is 5, as 5 times 7 is 35, and you see that this will never end. So you'll get 5, 7, 1, 4, 2, 8. So if you want 0.57142 and this repeats again. 57142 and again and again and again forever. So just as in the case of 1 over 6, we have an infinite decimal expansion that is cyclic, that repeats itself forever, but the pattern is a lot more interesting. 1 over 6 was simply 0.16 forever, but 4 over 7, and if you want we can write it here as our conclusion, is in decimal form exactly 0.571428 periodic. So where this pattern, again, repeats itself forever. So you can think of copy-pasting this down to your right forever. So hopefully this was a good reminder of how to perform any division by hand, and again reminding yourself that sometimes the decimal expansion can be cyclic, can be periodic, and other times it has a definite ending. And that's it.